Hello everyone, this is Xinyao Yu from the Visualization Research Center at University of Stuttgart. Today I'm very honored to present our work, Design Space of Visual Feed-Forward and Corrective Feedback in XR-based Motion Guidance Systems, which was also contributed by my colleague Benjamin Lee and my supervisor Professor Michael Sidmeyer. As we know, XR has been widely used in the domain of motion guidance systems, which assist individuals in learning and achieving specific motor skills, postures, or movements. Concretely, by presenting motion feed-forward and corrective feedback around or even on the trainee's body, motion guidance systems avoid sloppy or incorrect performance of motions in the absence of instructor supervision. While there are many XR-based motion guidance solutions, there is still a lack of synthesized answer to the key questions in designing such systems. For instance, how the motion instructions are presented, how the system responds to user interaction, and how to help users rectify errors. To address these questions, in this paper, we explore the design space of XR-based motion guidance systems. In doing so, we structure our exploration into two components: motion feed-forward, providing motion instructions before the trainee has taken action, and the corrective feedback, adding in behavior correction and performance improvement in response to the trainee's actions. To ensure that our design space is properly grounded in prior XR-based motion guidance research, we conducted a literature review. Specifically, we use the snowballing approach. Our start set consists of 3 parts: 2 survey papers, publications with over 100 citations on Google Scholar, and typical publications within the past 5 years. Our backward snowballing stopped at 2002, when the first VR-based motion guidance system named Just Follow Me was published. In the end, our final corpus consists of 38 papers. The feed-forward provides information on how to move or perform specific motions. For this, we propose 4 dimensions: level of interaction, interactive update strategy, viewing perspective, and additional contextual cues. For the first dimension of design space, we describe 3 levels without strict boundaries between them. Each of them refers to a different possible level of interaction in a frame. Explicit usually provides a clear posture for trainees to imitate, with a low ambiguity. Implicit provides cues like path or end spots for trainees to interpret and infer the motion details, which carries medium ambiguity. Abstract shows little cues about how to exactly perform the motion, requiring trainees to approximate the motions as best as they can. As for our second dimension of feed-forward, we focus on the interaction between trainees and feed-forward, and hence propose interactive update strategy. Concretely, motion guidance systems often employ checkpoints throughout the motion sequence, progressively updating parts of the feed-forward in response to the trainee's movement as each checkpoint is reached. In the discrete strategy, the checkpoints are only located at critical postures. While in continuous strategy, checkpoints are distributed throughout every single frame of the motion sequence. Lastly, the movement feed-forward may also update autonomously without responding to trainees. The third dimension, viewing perspective, affects trainees' perception of both the feed-forward and their own bodies. This can be first person, which is the most intuitive as in our natural life. The mirror perspective, which is used in dancing tutorial or physiotherapy. And the third person, which is often used in role-playing video games. Lastly, in addition to the spatial temporal information about the motion, the feed-forward needs to provide some additional information of the motion, such as the movement speed during dancing and muscle activation level in leg rehabilitation. As another important branch of our design space, the corrective feedback provides alerts, reminders, and advice to trainees about the errors they make during training. To better investigate this space, we classify corrective feedback into two major groups: intuitive and additional. The intuitive feedback is derived from the feedforward, when the feedforward carry a low level of interaction such as explicit and implicit. The trainees can directly notice the disparities between feedforward and their own movements, which is intuitive. Likewise, feedforward can indicate a binary error report when responding to the trainee's interaction. When the visual feedforward is not updated, it means that the trainee's posture is not correct. However, this intuitive feedback may be insufficient and limited, such as for the depth perception or in the multi-limb scenarios. That is why we need additional feedback. For additional corrective feedback, we intended to structure the design space into information level, temporality, placement, and presentation, which correspond to what, when, where, and how. The corrective feedback typically falls under three progressive levels of information. Detection feedback is straightforward and binary. Magnitude tells the trainees the extent of the deviation from the target posture. Rectification feedback will provide trainees with suggestions to refine their movements. The additional feedback can be presented in real time or post hoc for analysis or suggestions, as you can see in the picture. As for placement, the corrective feedback can be embedded into the feedforward, situated at the trainees, or stationed in the environment. For the presentation of corrective feedback, instead of focusing on the specific visual cues like a previous work, we focus more on common attributes of visual cues. Through the visual pre-attentive mechanism, we found these visual attributes may take the form of color, direction, or size, and may also be reflected in the content of text or graph. Now we used our design space to describe the existing technical setups. We identify an example from the literature and describe how they are set up in our design space. In this video, the feedforward is the movement trajectory of the arm, and changes color with completion, which is implicit. The feedforward takes a continuous update strategy in the first-person perspective. When the deviation happens, the real-time rectification feedback presents size-changeable cones between the feedforward trajectory and the trainee. The higher deviation will evoke a longer, wider, and redder cone. We did the same thing for all 38 papers in our corpus and eventually found 56 technical setups. We also summarized the common design approaches from these setups, such as the relationship between feedforward, feedback, and user scenarios, the relationship between different dimensions, and future opportunities for visual cues. More details can be found in our paper. Next, we illustrate how to use our design space to create new XR-based motion guidance systems. We take British Sign Languages as an example. In this case, the trainee needs to observe clear gestures, which means the feedforward should be presented explicitly and in a discrete strategy. Traditionally, sign languages instruction is presented by the trainer in a third-person perspective. However, since all the sign languages movement take place in the frontal area of the trainees, the designers can also attempt to employ the egocentric features of XR by using first person. As for feedback, the designers can use color for misalignment of joints and the directional arrow to point where to move. However, the text feedback may be chaotic due to too many joints on the hand, and the graph can be used to visualize the completion time of consecutive gestures. At last, we briefly discuss the related constraints and factors to make our design choices. The first factor we should consider is the features of the motion itself. The higher speed and more involved limbs will increase the cognitive cost during training. while the motion area is related to the perspective. For instance, it is tricky to use the first-person perspective to present a movement happen behind your body. The second factor is the objective scoring framework, which presents overall assessment feedback after training. For instance, if the trainer cares about the performance of every moment of the training phase, then the scoring framework is supposed to include an evaluation of every frame of the training's movement, and a continuous update strategy should be used. Everyone has unique physiological traits, cognitive abilities, learning styles, and emotional factors, which impact their progress in motor learning. So, personality of motion guidance is necessary. For example, specialized movements should be recorded for patients with limb injuries and adjusted regularly as rehabilitation progresses. The last factor we consider is the similarity in appearance between trainer and trainee. Given that motion guidance tasks inherently contain elements related to visual search and matching, we argue that the similarity in appearance between avatars and feed-forward instructor can influence training's performance. That's all. Thank you for listening.